So question number 12 says, lights of two different frequencies whose photons have energies 2 eV and 10 eV respectively successively illuminate a metal of work function 1 eV. What is the ratio of the maximum speeds of the emitted electrons?
Yeah, so here we need to find the ratio of the maximum speeds.
Mm-hmm.
So before the maximum speeds, we have a ready-made formula that
Okay.
is for the maximum kinetic energy.
H nu minus work function?
Yeah,
Mm-hmm.
that. So we have K max equals to H nu minus W naught, which is the work function.
Yes.
And it is equal to half
mv square.
V max
V max square. Yes.
Here V max, because maximum kinetic energy electrons would be the fastest ones and have the maximum velocity.
And that's what they've asked us to find.
Yeah. So this thing half mv square is directly there in classical mechanics.
True.
Kinetic energy equal to half mv square.
Mm.
So we have been given E1 equals to 2 minus 1 equals to 1 electron volt. This 1 is because the work function is 1.
Right.
Similarly, E2 equals to 10 minus 1,
which is
9 electron volts.
Uh-huh.
So here we are nearly very close to finding the final answer, that is the ratio of the velocities.
Right. So can I tell you if this I'll tell you the approach and can you tell me if it's right or wrong?
Yeah, okay.
So basically what I know from now is that we have the relation K max is equal to half mv max square.
Yeah.
And then we have both the values of E1 and E2.
Yes.
And the masses in fact are the same. Right, so once we take the ratio of E1 to E2,
yes,
the masses get cancelled.
Yeah, so we don't need to actually take the mass into consideration.
Exactly. So
it's the same.
Right. So do we proceed by taking ratios and then finally getting a ratio of the final
whenever
speeds?
There's a question of finding ratios, it is easiest to take the ratio as early as possible so that the similar terms get cancelled.
Yes.
Yeah, so we take it as E1 by E2 equals to 1 by 9,
which is equal to half
half
mv max
V1 max
square
by half mv2 max
square.
So here we see that this half and this m are similar, so they get cancelled.
Yes.
And next, these both terms are square terms.
So we can take the root of the whole.
We can take the root of the whole, and it will be 1 by 3 equals to V1 max
by V2
max.
And this is all they've asked us to find, right?
Yeah. So the answer is 1 by 3. That is the required ratio.
So all you need to remember is that you do not need to find the velocity of the electron as such. You just need to find the ratio. So you should avoid using a lot of time and wasting time on such lengthy calculations.
Like you could have done the calculation here and found the maximum velocity for case 1 and case 2, and then taken the ratio.
And that would be very
very long and tedious job with a lot of calculation, but you would have arrived at the same answer, that is 1 by 3.
Right. So the final answer, the required ratio of the maximum speeds of the emitted electrons is 1 by 3. So that was question number 12. So coming to question number 13, a monochromatic light source of frequency f illuminates a metallic surface and ejects photoelectrons. The photoelectrons having maximum energy are just able to ionize hydrogen atoms in ground state. When the whole experiment is repeated with the incident radiation of frequency 5f by 6, the photoelectrons so emitted are able to excite the hydrogen atom beam, which then emits radiation of wavelength 1215 angstrom. What is the frequency f of the radiation, and find the work function of the metal?
So moving on with this problem, first of all, we know that to ionize a hydrogen atom from the ground state, the energy that is required is 13.6 eV.
True.
This you need to remember, as this is a constant, and this comes into use in many problems.
Okay.
So you need to remember this. This is the energy E required to ionize a hydrogen atom from the ground state.
Okay.
So since in the first part it is given that the maximum energy electrons can ionize this, so it is K max equal to 13.6 eV.
Right.
That is
H
HF.
nu, yeah, HF.
F is the given frequency.
Right.
Minus
HF.
W equal to 13.6 eV.
True.
We keep this as equation 1.
Mm-hmm.
Next case is given H 5F by 6. This is the new frequency.
Yes, minus work function.
Work function equals to 12375 by 1215 Armstrong. 1215 Armstrong is the wavelength of the radiation emitted by the hydrogen beam. And this is the formula that is given in the theory part of this course.
Okay.
That to find the energy, just divide 12375 by the wavelength in Armstrongs.
Okay.
This will give you the energy. This is a basic formula that you need to remember.
Okay.
Which will give you 10.2 eV. This formula gives the energy in electron volts.
Okay.
So we take this as equation 2.
Okay.
Next we do
so basically what we have done so far is that we have found out two equations.
Yeah.
The first one being of frequency F, the second one for 5 by 6F.
Yeah, 5 by 6F.
Okay.
And so with this we can proceed by subtracting the equations.
Right, because work function gets cancelled.
Work function gets cancelled. 1 minus 2 gives us H into F by 6. Since F minus 5F by 6 gives F by 6. And work function itself gets cancelled. And so like subtracting these two parts, we get equals to 3.4 electron volts.
Right.
So H into F by 6 is 3.4 electron volts, which gives us F by simple substitution 6 into 3.4. We convert electron volts into joules by multiplying with
1.6 into 10 power minus 19.
Yeah.
Whole divided by the Planck's constant.
Yeah, divide by H, which is 6.63 into 10 raised to power minus 34.
Right.
This is the Planck's constant. And with this, we get the first part of the problem. The answer to the first part, it is 4.92 into 10 raised to the power 15 hertz.
Right.
This is the frequency F, which was asked in the first part of the question. Part A.
Right. So basically, how did we find out the solution? The first part, we had to remember the fact that 13.6 eV is the energy required to ionize a hydrogen atom from the ground state, right?
Yeah.
And then we found out two equations based on our usual age-old formula: E is equal to HF minus work function. And these two equations together, when we subtracted them 1 minus 2, gave us the frequency F, which was asked from us to find out. So frequency F was 4.92 into 10 power 15 hertz. So right, what about the work function right now?
Yeah, the next part
we just
is
substitute one into the
work
one
function. We can substitute the work function in equation 1, and W equals to HF minus 13.6. We know H, we know F here. So just simply substitute the values to get 6.8 electron volts, which is the work function.
Right. So again, most of the time, most of the work was done when we found out the value of F. All we needed to do was substitute the value of F in one of the equations 1 or 2, and we'd prefer to put it in the equation 1 because we can avoid fractions like 5 by 6, which might just elongate our time of getting closer to the solution. So finally we arrived at the work function, which was 6.8 eV. So this was question number 13, and it was pretty straightforward, but it just needed a few things, like probably remembering the value 13.6 and probably just making sure that you apply equations like these and subtract them because you do not know the value of W as such.
So in this chapter, the things that you need to remember are the formulas and some constant values, because they are used in most of the problems. And if you do not remember that, you cannot move ahead in the problem, and you'll get stuck in the first step itself, and you won't find the way to solve this problem. So it is very important that you remember all formulas, shortcuts, and the constant values.
Right. Okay, thanks a lot.